Hi class, this is Mrs. No, and I'd like to give you a short video lesson about naming and writing ionic formulas. So today's target is to learn how to electrically neutralize ions in ionic formula and then naming the whole ionic compound. So let's begin with the word electroneutrality. So what is electroneutrality? By definition, electroneutrality means balancing the charges of ions in an ionic compound to have an overall net charge of 0. So you take a look at these two ions. This is gallium 3+, and this is sulfate ion, the one that you memorized, SO4 2-. You look at these two charges currently do not balance out. And so what we need to do is add more of each of those ions in order to, until the point that they balance out to a net charge of 0. So let's go ahead and balance those charges out. I have gallium 3+ and sulfate ion right here. So we need another sulfate ion in order to balance out the positive charge that you see in gallium 3+. But now you see that there's more negative charges. If you add up these two negative, you get a -4. And then against a +4, there's now more negative. So you need now more gallium 3+ ions. So you add one more, and in adding one more, you'll notice 6 positive charge with the two galliums, and then a -4 charge with the two sulfate ions. Once again, you now have too much positive here, positive charges, and so you need now another negative charge. And so you add another sulfate ion. Now if you add up all the charges, now they completely neutralize each other. The positives neutralize with the negative charges to give you a net charge of 0. So now the chemical formula written out for this ionic compound is as such. By the way, you should notice that it's ionic between the gallium and the sulfate, but then it's covalent within the sulfate. And that's where this ionic compound has both ionic bonds as well as covalent bonds within the sulfate ion. That's going off topic a little, but the formula that you form out of this compound is there's 2 GAs, so 2 gallium ions, and then there's 3 sulfate ions. So to write out that formula, you would write it out as such: Ga2 parentheses SO4 and parentheses 3. Now notice that I put parentheses around the sulfate ion. Without them, what happens is you end up looking like you have 43 oxygen atoms. And that is not truly the case. And there is not an existing atom that would look like that between gallium and sulfate. So that's why you need parentheses around this whole group of atoms, this polyatomic ion. The name of this is, if you look on this chart right here, this chart shows all the metal cations with d orbitals requiring Roman numerals. So I decided to highlight all the ones that you would have to kind of take notice. Notice none of the s orbital metals require Roman numerals, and none of the anions, your p block nonmetals, would not need Roman numerals. It's only your metals and some of your metalloids that need Roman numerals. The exceptions are zinc, cadmium, and silver. We never do the lanthanides, so don't worry about those, but they also do not have more than one charge. They only have one charge, and that's usually a 3+ charge. The actinides have multiple charges, but we don't oftentimes see them bonded with other elements in an ionic bond. So going back, gallium is highlighted right here, which means that gallium requires Roman numerals. So what charge does gallium have? So looking at the original compound, it has a 3+ charge. So we would be writing gallium with a Roman numeral 3 to represent that 3+ charge. So the Roman numeral reflects the charge of the ion in the ionic compound. specifically the metal cation. Sulfate, if you look at the anions, the sulfate ion is actually never modified. You never modify that name, so it's just called sulfate, gallium-3 sulfate. Let's do some examples, some more example problems, writing chemical formulas. Starting off with example 1. If you look at this is silver sulfide. Silver is located right here, doesn't require Roman numerals, and that's why you do not see Roman numerals in the name of this compound for silver. And so if you look at silver, silver has a charge of +1. Remember how to find the number of valence electrons using that group numbering system. And plus, remember that silver is like copper in the sense that it has that exception to the off-bow principle, where one of its electron from the 5s hops over to the 3d, filling up its 3d, leaving only one electron in the 5s. So silver has only one electron that it tends to lose because it's a metal. So silver has a 1+. Sulfide is a monatomic ion. So sulfide's right here, and it tends to gain 2 electrons to be isoelectronic with the argon. And when that happens, you have the following 2 ions. To neutralize those 2 ions, you need to add another silver ion, giving you Ag2S. Ammonium bromide, in our second example, ammonium is not located on the periodic table. If you try looking for it, you won't find it because it is a polyatomic ion, but it is a cation. It's a cation, a positive charged polyatomic ion. So why don't you take a second and look at your pink sheet and find ammonium listed on the top of your list of common ions. So you'll notice that ammonium is NH4 with a +1 charge. Now bromide is also a monatomic ion because it has an "ide" ending. So we know that it has, bromide will gain 1 electron to be isoelectronic for krypton. So the 2 ions that you will have to start off with would be the following 2 that you see here. And to balance those 2 charges, they're really nicely balanced out. If you put 1 of each of those ions, gives you NH4Br. Looking at the next one, example 3. Notice that nickel here, nickel 2, has Roman numerals because, again, nickel is one highlighted as far as the metal cations with d orbital. And so nickel starts off with a 2+ charge. Phosphite took a bite of oxygen because it has an "ite" ending, meaning it's a polyatomic ion that you memorized, and it's PO3 3-. So looking at these 2 charges, you'll notice that they don't balance out quite right off the bat, so you'll have to then find a common multiple between the 2. The common multiple between 3 and 2 is 6. So in order to get 6 positive charges over on the cation end is to have 2 more of the nickel 2+ ions, giving you a total of 3 nickel 2+ ions. In order to get a -6 on this side, you need 2 of these phosphite ions. So in having 2 of these phosphite ions, you will now have a -6 overall charge on the negative anions. And so the formula will be Ni3, because you tripled up the nickel 2+ ion, and then you doubled up the phosphite ion, and so you will see the phosphite ion doubled up right here with the parentheses around it because you're grouping the whole polyatomic ion. So let's move on to naming chemical formulas. Naming chemical formulas is just using your simple naming rules. You first start off with your metal cation, and noticing that magnesium doesn't require Roman numerals. You do not need to use Roman numerals for magnesium, so we call it magnesium. And then we name the anion, which is chloride. So this is chloride ion. So magnesium chloride is what you call this first example. In the second example, You have copper and you have a polyatomic ion. Hopefully you recognize that this polyatomic ion is bicarbonate, or you can call it hydrogen carbonate. But copper, you should always check to see if it's one of your d orbital elements that require Roman numerals, and it is. So copper's Roman numeral charge can be determined by the anion that it's with. Because bicarbonate has a -1 charge, and there's 2 of them, that means overall the anions take on a -2 charge. Copper must have a +2 charge in order to balance out that -2 charge. So we know that the name for this compound is copper 2 bicarbonate or copper 2 hydrogen carbonate. So we go to example number 3. In example 3, again, tin. I look up tin and I see that tin is one of the highlighted ones, so I'm going to need Roman numerals for tin. But to know what tin's charge is, again, you look at the anion to help determine the charge. So arsenate has a charge of 3-. Because you have 2 of them, giving you -6, the charge for the cation must be +6. So that means that each tin must be, if it's +6 for all 3 tins, each tin must have a charge of +2. So we call that tin 2 arsenate after you've realized what tin's charge is. I hope this video helps. We will practice much more coming into class before we take our naming ionic and writing formulas for ionic compound quiz.